Risk assessment is not paperwork, and it is not a form you complete after a machine is already designed. It is a design discipline. If you wait until the layout is frozen, the equipment is selected, the control philosophy is written, procurement is moving, and the project is under schedule pressure, then you are no longer performing risk assessment at the right time. You are trying to protect people from hazards that should have been challenged much earlier. That is the uncomfortable truth. Too many engineering teams discover risk late and then start adding guards, trips, alarms, interlocks, warning labels, procedures, and training around a weak design. The machine may become compliant on paper, but the architecture remains complicated, expensive to maintain, and vulnerable to bypass, degradation, and hidden failure. You should not begin by asking, which safeguard do we need? You should begin by asking, why does this hazard exist, and can we remove it? That single question separates reactive safety from good engineering. As a design engineer, discipline engineer, lead engineer, automation engineer, maintenance engineer, or operations engineer, you are not merely selecting components. You are creating the conditions under which people will interact with moving parts, stored energy, pressure, electricity, heat, chemicals, automated sequences, and abnormal machine behavior. Your responsibility is not limited to whether the machine works. Your responsibility includes how the machine fails, how people intervene, how energy is controlled, how protection degrades, and what happens when assumptions collapse. A machine is not safe because it has an emergency stop. It is not safe because it has a light curtain. It is not safe because it has a safety controller. It is not safe because the risk register is complete. A machine becomes safer only when its hazards are systematically understood, its risks are reduced through design, its remaining safeguards have sufficient integrity, and the complete protection strategy continues to work during operation, cleaning, setup, maintenance, fault recovery, modification, and dismantling. The first distinction you must get right is the difference between hazard and risk. A hazard is a potential source of harm. A rotating shaft is a hazard. A crushing point is a hazard. Stored hydraulic pressure is a hazard. A live conductor is a hazard. A hot surface is a hazard. A suspended load is a hazard. Unexpected movement is a hazard. Risk is different. Risk is the combination of how serious the harm could be and how likely it is that the harm will occur. That distinction matters because many hazards are inherent in the function of the machine. A press must exert force. A cutter must cut. A robot must move. A compressor must contain pressure. A furnace must generate heat. You may not be able to remove the basic energy that makes the equipment useful, but you can engineer the interaction between that energy and the exposed person. That is where risk reduction lives. At its core, every machinery risk assessment is trying to answer two questions. How bad could the consequence be? How likely is it to happen? But likelihood is never just one number. It is influenced by how often someone enters the hazardous area, how long they remain there, whether the event is predictable, whether escape is possible, whether the hazard develops slowly or instantly, whether the protection detects faults, whether the machine can restart unexpectedly, and whether the task encourages shortcuts. Human factors are also part of the calculation. People get tired, people become familiar with danger, people work under production pressure. People bypass inconvenient safeguards. People improvise when access is poor. People misunderstand unclear instructions. People stop noticing deterioration during repetitive work. A risk matrix cannot understand any of this unless the engineer using it understands it first. That is why a risk score is not the risk assessment. The score is only the output of engineering judgment. A precise number built on weak assumptions is still weak engineering. Before you identify hazards, you must define the limits of the machine. What is the intended function? What is the speed? What forces are involved? What pressures exist? What temperatures are reached? What is the movement envelope? Who will operate it? Who will maintain it? What operating modes exist? What abnormal modes exist? What happens during startup? What happens during shutdown? What interfaces exist with other equipment? What is the expected life? What foreseeable misuse could occur? That final question is essential. Foreseeable misuse is not the same as deliberate recklessness. It includes predictable human responses to poor design. If a guard must be removed every 2 minutes, someone will eventually defeat it. If resetting the machine requires an unnecessary delay, someone will search for a bypass. If maintenance access is awkward, improvised methods will appear. If nuisance trips are frequent, the protection will lose credibility. If the procedure conflicts with production reality, the procedure will not survive. Good engineering does not assume perfect behavior. It anticipates ordinary human behavior and designs around it. The next major mistake is focusing only on normal operation. Many serious incidents happen when the machine is not operating normally. They happen during cleaning. They happen during jam clearing. They happen during fault recovery. They happen during commissioning. They happen during setup. They happen during maintenance. They happen during modification. They happen during dismantling. The machine must therefore be assessed across its entire life cycle, from manufacture and transportation to installation, commissioning, operation, maintenance, and final disposal. A machine that appears safe in automatic mode may become highly dangerous the moment a person opens a guard to remove a blockage. A motor may be electrically isolated while hydraulic pressure remains. A pneumatic actuator may retain stored energy. A suspended load may remain supported only by pressure. A machine may stop while gravity, heat, tension, or compression remains active. Switching off control power is not the same as removing hazardous energy. This is why operations and maintenance engineers must be involved early. They understand where people will stand. They know which access points will be used. They know which tasks are repetitive. They know which safeguards are inconvenient. They know what happens when the plant is under pressure to restart. A drawing shows intended behavior. Operations reveal actual behavior. Once the limits are defined and the hazards are understood, the hierarchy of risk reduction must be applied in the correct order. First, eliminate the hazard by design. Second, reduce the magnitude of the hazard. Third, introduce engineered safeguards. Fourth, communicate residual risk through warnings, procedures, and training. Do not reverse that order. A warning label is not stronger than a design change. A procedure is not stronger than physical isolation. Training is not stronger than eliminating the hazard. Human behavior should not become the primary control where severe injury is possible and a stronger engineering solution is reasonably achievable. The best safeguard is often the hazard that no longer exists. A trapping point may be removed by changing geometry. A shear point may be removed by redesigning the mechanism. A manual loading hazard may be reduced through automation. A dangerous movement may be limited through lower speed or force. Exposure may be removed by relocating an intervention point. Stored energy may be reduced through system design. These changes are often simpler, more reliable, and cheaper over the equipment life than adding layers of complex protection later. Every additional protective layer creates new components, new failure modes, new test requirements, new maintenance tasks, and new opportunities for bypass. When elimination is impossible, reduce the hazard before safeguarding it. Question the design parameters. Does the actuator really need that force? Does the machine really need that speed? Does the operator really need access every cycle? Can the movement range be limited? Can stored energy be reduced? Can the process be reorganized so intervention is less frequent? Design engineers create enormous safety value when they challenge inherited assumptions rather than treating every process requirement as fixed. When hazards remain, safeguards become necessary. These may include fixed guards, interlocked movable guards, presence sensing devices, pressure-sensitive systems, trip devices, two-hand controls, and other protective measures. But a safeguard must do more than exist. It must work under realistic conditions. It must be correctly positioned. It must account for stopping time. It must resist foreseeable defeat. It must not create new hazards. It must remain effective after wear, contamination, vibration, misalignment, and maintenance intervention. A badly designed safeguard may technically reduce access while creating operational frustration. That frustration becomes bypass pressure. This is why usability is part of safety integrity. A protective device that works perfectly in theory but is routinely defeated in practice is not a successful design. Every risk reduction measure must also be reassessed because controls can create new hazards. A guard can create a new crushing point. An enclosure can restrict escape. An interlock can produce unexpected restart behavior. A light curtain can be placed inside the stopping distance. Automation can remove operator exposure while creating maintenance exposure. A new control circuit can introduce hidden dependencies. The question is never only, did we control the original hazard? You must also ask, what new hazards did the solution create? This is why risk reduction is iterative. You identify, you assess, you eliminate, you reduce. You safeguard, you reassess, you verify, then you repeat the cycle whenever the design changes. Risk scoring can support this process, but it can also create false confidence. A practical assessment may consider likelihood of occurrence, frequency of exposure, degree of possible harm, and the number of people exposed. These factors help prioritize actions, but the numerical result is not a measured physical truth. It is a structured judgment. The value comes from the reasoning, not the arithmetic. You should always document why each factor was selected. Why is the event considered unlikely? How often is the person really exposed? What is the worst credible injury? How many people can be present? What happens during abnormal operation? What evidence supports the assumptions? If a severe consequence becomes acceptable only because someone assigned an extremely low likelihood, challenge that decision hard. Ask what makes the event unlikely. Ask whether the safeguard is already being credited. Ask whether the assessment ignored maintenance. Ask whether bypass was considered. Ask whether failure history supports the judgment. Never let a low number silence engineering concern. A useful method is to assess the raw hazard before taking credit for the existing controls. This reveals the inherent risk. If a person can repeatedly reach into an area containing high force motion, then the uncontrolled risk may be high even if a guard currently exists. You then compare the existing protective measures against the level of protection required. This prevents the team from assuming that some protection automatically means sufficient protection. After controls are added, the hazard must be reassessed. In many cases, the severity of harm remains unchanged. The safeguard only reduces the probability of exposure. That means the integrity of the safeguard becomes directly related to the seriousness of the consequence. If failure of one switch can expose someone to fatal or permanently disabling harm, the issue is no longer only mechanical guarding, it becomes control system integrity. You must understand the complete safety function. Which sensor detects the condition? Which logic processes the signal? Which final element removes the hazard? What happens if a contact welds? What happens if a valve sticks? What happens if a wire breaks? What happens if an output remains energized? What happens if a fault stays hidden? What happens if two faults accumulate? What happens if both protective channels share the same cause of failure? This is where many assessments become shallow. They specify an interlock without analyzing the architecture behind it. Using a high-quality component does not automatically create a high-integrity safety function. A reliable component can still fail. If one failure removes the entire protective function, the architecture remains vulnerable. Component reliability and system fault tolerance are not the same thing. More demanding safety functions may require proven design principles, periodic checking, fault detection, redundancy, and protection against common cause failure. Redundancy is powerful, but two channels are not truly independent if both can fail from the same cause. Two sensors can fail from the same contamination. Two cables can be damaged in the same tray. Two devices can lose the same power supply. Two identical components can suffer the same environmental stress. The important question is not whether you have two channels. The important question is whether those channels are sufficiently independent to provide real protection. Fault detection also changes the safety equation. A detected fault can drive the machine to a safe state. A hidden fault can remain dormant until another failure occurs. This is why diagnostic coverage matters. But diagnostics must also be questioned. How is the diagnostic function tested? Can it fail silently? How frequently is it exercised? Can the machine continue operating in a degraded state? Who is alerted? What action follows? A detected fault that is ignored is not an effective safety measure. Fail-safe design must also be understood physically, not rhetorically. A system is not fail-safe because the drawing says fail-safe. It is fail-safe only when foreseeable failure causes the process to move toward or remain in a safer condition. Stopping motion may be safe in one machine, but dangerous in another. Closing a valve may isolate a hazard in one process, but create overpressure elsewhere. Removing power may stop a motor while allowing a suspended mass to fall. The safe state must be defined at system level. You must know what the equipment physically does after the failure. Maintenance deserves separate attention because maintenance conditions are rarely equivalent to production conditions. Guards may be open, interlocks may be bypassed, stored energy may remain, personnel may enter restricted spaces. Multiple energy sources may exist simultaneously. The isolation strategy must address electrical, hydraulic, pneumatic, mechanical, thermal, and gravitational energy where applicable. The correct question is not, has the machine stopped? The correct question is, can hazardous energy still reach the person performing the work? Training remains necessary, but it must not become a repair for bad design. Training should support engineered protection. It should not replace it. If severe injury is prevented only by expecting someone to remember a procedure perfectly every time, the protection strategy is weak. Warnings, procedures, and training belong at the end of the hierarchy, not at the beginning. Management also has a direct role in machinery risk. Risk is shaped by budget, schedule, layout decisions, procurement strategy, responsibility boundaries, commissioning pressure, and maintenance philosophy. When risk assessment is delayed, projects lock themselves into expensive corrective action. Early risk reduction is design efficiency. Late risk reduction is project recovery. Risk assessment should therefore be connected to design gates. Major hazards should be understood before concept approval. Risk reduction strategies should be defined before detailed design. Safety critical requirements should be included before procurement. Safeguards should be verified before commissioning. Residual risks should be communicated before handover. Changes should trigger reassessment after startup. The final test of a risk assessment is not the number of pages it contains. The test is whether the engineering team can answer difficult questions clearly. What can hurt someone? Who can be exposed? When can exposure occur? What is the worst credible consequence? Can the hazard be eliminated? Can the energy be reduced? What prevents the event? What happens when the protection fails? Will that failure be detected? Can faults accumulate? Can the safeguard be bypassed? What happens during maintenance? What happens during fault recovery? What changes require reassessment? If these questions cannot be answered, the assessment is not mature. The strongest design engineer does not simply ask whether the machine will work. The strongest design engineer asks how the machine can hurt someone, how the protection can fail, what happens next, and what can still be changed before someone discovers the weakness through an incident. That is the real purpose of machinery risk assessment. It is disciplined anticipation of failure before failure becomes injury. Design the hazard out before you engineer the safeguard. Reduce what remains. Protect against what remains. Challenge the protection itself. Reassess after every meaningful change. And never allow documentation to replace engineering judgment. Share your experience in the comments. Where have you seen risk assessments fail most often? Late design involvement, weak hazard identification, unrealistic scoring, poor maintenance access, bypassed interlocks, hidden control faults, or excessive reliance on procedures. What design change have you seen eliminate a hazard more effectively than layers of protection? Add your opinions, lessons learned, and practical engineering principles, because the strongest safety knowledge often comes from understanding where design assumptions failed in the real world. Like this episode, share it with engineers, project managers, and technical leaders who need to hear it, and subscribe to the channel for more practical discussions on engineering design, automation, project execution, functional safety, and engineering management. Follow my LinkedIn newsletter for deeper standards and recommended practices. Simplified articles created for discipline engineers, lead engineers, design engineers, and operations and maintenance professionals. Strong design today creates safer operations tomorrow.